let's go ahead and get started. I think the technology is finally working for us here. Um, we left off kind of in the middle of talking about both just unified shader architectures in general and the CUDA programming programming model. And this concept, which I talk about, is partially marketing and partially a novel architectural concept, is this SIMT. And I wasn't sure to what extent. It depends on when you took 381 and and to what extent that semester there was time to cover this as a separate topic. To what extent you understood this acronym space for computer architecture. It's not in and of itself a fundamentally important concept. It's two parts of the acronym that refers to the instruction stream and the data stream. So it's something I, something D is that alphabet soup that we wind up describing. Where for most of the programming you've been just writing sequential code executing in a single thread. You've been doing some multi-threaded stuff, but for very traditional introductory programming, you've been doing single instruction, single data, where there's a single we assemble our code down to a single scalar instruction. There could be some pipelining that has some overlap and some parallelism there, but in generally we're doing one thing at a time. And we have compilers and we have pipelines that allow us to do that one thing at a time relatively effectively. In 381, again, depending on when you took it and how much focus there was in that particular semester, we also talk a decent amount about SIMD or SIMD, and that's single instruction multiple data. And the idea at SIMD is that for a given instruction, you're doing multiple things in parallel. There's other acronyms we can talk about as well, but for SIMD, generally what we're doing is one operation across parallel lanes of data. And part of that is an ISA thing, right? Does our ISA express that parallelization or parallelism for us to potentially exploit it in our microarchitectural implementation? Vector add, right? Instead of a regular add, we're instead taking perhaps the same register, splitting it up into four different 8-bit lanes, and doing four of those additions in parallel. That's an ISA specification. Now, when it's our turn to actually implement that microarchitecturally, we've already seen that a little bit with our shader cores we've implemented in the lab. We may have an ISA that specifies a vectorized instruction, a SIMD style instruction, but when we then go to implement it, we may realize that the trade off between resource usage and performance may make it not as worthwhile to actually implement it in parallel. So in 3D, we talk a lot about ISA versus microarchitectural, the assembly instructions and what they're supposed to do versus how we actually implement them. SIMD refers to both, but usually it's encoded at the ISA level. We have vector add or vector multiplication, and it's doing these things in parallel. When we start to talk about these streaming multiprocessors, for which the NVIDIA GPU architectures are all built around, we have this scalable array of these multi-threaded streaming multiprocessors. So we have this CUDA program. It's invoking a kernel grid, and then the blocks of the grid are enumerated and distributed to these different streaming multiprocessors listed as SMX on this particular slide for this Kepler class architecture here. So the threads of that thread block are what are executing concurrently on one of those SMs at a time. And potentially, depending on our resource utilization here that we'll talk about in a moment, potentially you have multiple thread blocks executing concurrently on one SM at a given time. And when a thread block terminates, then the next thread block can be launched and then on whatever has been vacated on that streaming multiprocessor. The idea with the design of these is to execute hundreds or potentially thousands of threads concurrently. And to manage that relatively novelly large amount of threads, this architecture is referred to as single instruction multiple thread or SIMT. Um, the instructions are pipelined like you would have learned about in 381. So you have your basic instruction level parallelism that we already do in 381. But we have this fairly extensive thread level parallelism through this kind of hardware multi-threading. Unlike the more advanced things, if you take a 581 type of course that you would learn about doing speculation, advanced branch prediction, reordering of instructions, these cores by and large themselves are relatively simple. But what they do is by having a single thread, a single kernel invoked at a given time, allow us to share a lot of resources between those threads. So it's very similar to SIMD in the sense that we have vector add style instructions, but what makes it different than SIMD in which we have to explicitly program that or have a compiler that can generate that for us. We can write our threads from our kernels, excuse me, from a single thread's perspective, and the architectural layout of these SMs allow us to switch between them and then to run as many as hundreds or thousands of them at one given time. So we'll continue to talk about that, but that's just a little bit of the alphabet soup here with regards to SIMT versus SIMD. Um, Main takeaway I think would be relatively simple SIMD style cores. So a lot of what you learn about, let's say, modern Intel microarchitecture gets ripped back out and not used for this style of implementation. But then, because of some assumptions both about the workload, which is a single kernel, everything is executing the same assembly code, and then also some assumptions about how we do register allocation and things like that, allows us to handle thousands or hundreds to thousands of threads at one given time. So single instruction multi-thread, arguably it's a little bit of marketing what it really is. A highly multi-threaded SIMD style architecture in which we restrict what the threads can look like. And consequently, because of that restriction, you can execute so many more of them than you would be able to feasibly do on a traditional SIMD microprocessor implementation. We can talk about the register file. So again, as part of that SIMT or SIMT, you have this execution context, right? This idea that you have the data associated with a thread. That is what keeps that thread valid. So when we switch between a thread to another thread, we have this context, and you learn about in a 308 style class, you learn about, or ComSci 352, you learn about a context switch. Well, for the SIMT, the execution context, that's your program counters, your program counter, your registers, others potential state, for a grouping of threads is maintained on chip during the entirety of that thread's execution. That is different than traditional microarchitecture, where we have a context switch and there's a cost associated with it. We at the very least have our program counter and our register file, and we say we're moving from thread A to thread B, and they're different. And because they're different, we have to take all the state out of the processor for thread A, store it somewhere in memory, take thread B's state, and then copy that back into the program counter and the register file and tell it to go. For SIMD, again, because each thread is executing from the same instruction stream, we can simplify that assumption. And the fact that it's being kept on chip is a relevant performance indicator here. So when we have that execution context, we can make a lot of those simplifying assumptions that, well, every thread needs the same amount of registers because they're all executing the same exact code. They can have some sharing of program counters between the threads. This is an implementation specific detail, but we'll talk about what grouping of threads makes sense in that context. No pun intended. Because of that, in doing a context switch, we can do things like, in this case, have a static allocation of registers in a register file and actually physically partition the register file. It's a logical partitioning, but do that partitioning at runtime so that the registers associated with group of threads A do not in any way overlap or conflict with a group of registers associated with thread B. And then because of that, because group of threads A, group of threads B, block A, block B, it's fine. You can use that term here. Because of that, you can actually then have multiple blocks of these threads executing concurrently on a device at a given time. And then consequently, also the switching between them becomes a relatively straightforward thing. None of the implementation docs actually talk about what does that really mean in practice to do that switching between one block of threads to another block of threads. But conceptually, at least to me, it makes a lot of sense that, again, this is an implementation detail that is quite a bit different than a traditional CPU. For the SM, you have very large register files. I would call, and this is an older device, a 64K register file is a pretty large register file. There's a bit of semantics here. Is it a register file? Is it a large memory? Well, we've talked about that a little bit in our implementation in our shader core. It's a bit of semantics, right? It's the same kind of functionality. You need to read from it. You need to write from it. Is it a big memory? Is it a large register file? It doesn't really matter, but it's a relatively fast local piece of storage that is shared between all the different thread blocks there. So while it doesn't necessarily say in any of the documentation exactly how that happens, from my perspective, the way it would probably work in the most logical fashion would be, again, the kernels are written from an individual thread's perspective, and so for this thread of block of threads here, it would just have this region of the register file allocated to it. And in going from block A or block 0 to block 1 to block 2 to block 3, the only thing that would change from an implementation perspective is somewhere there's a little bit of metadata that keeps track of that keeps track of, which block I am at runtime, not at compile time, but at runtime, which block I am, and consequently, what is my base register offset? So our addressing from the thread's perspective looks like I want register 27. But depending on how many total registers are being allocated to each thread block, and consequently which thread block I am, you'll take that value of 27, which is what the assembly is generating, and you'll add some constant offset to it. So it's register 27 then would then correspond to register 27 plus the yellow offset, blue offset, or red offset there. I mean, nowhere in the CUDA or NVIDIA documentation does it say that that's exactly what's happening, but to me, that's the logical solution here, that you have this static allocation of a large register file partitioned amongst the multiple thread blocks. And if things divvy up nicely, as shown on the left-hand side of the figure here, then you have that sort of constant base address that you're calculating. And so, just by the nature of the workload creation and the thread allocation and the register allocation in the compiler, you're never accidentally overwriting registers. That's not something that would happen then in practice. But because it is that static allocation, depending on how many registers we're going to need for any particular thread, I would imagine then, and some of the utilities help you kind of discover this, that if, for instance, this was our 64K registers on the left here, and each thread block used exactly 1/4, it used 16K registers for each thread block. That's not an unreasonable number. It depends on the number of threads in the thread block and the number of registers per thread. If we were to change our and then consequently, we can squeeze 4 things in here, right? We can have 4 thread blocks executing concurrently on the SM, and it's a little hand wavy, but more is generally better. If we can fit more threads on a device at a given time, and we have a parallel application for which the threads all have meaningful work to do, we should get better performance back out. But then the implication of this static partitioning scheme here, the programmer's view of our register file, is that if we were to tweak our code to add one more temporary variable, and this could be a compiler optimization change, or it could be you actually realize that you needed to calculate one more intermediate thing to get the correct result. So you've tweaked your algorithm in, let's say, a very trivial way to add one more register to the generated assembly code for it. Then I think it's very possible that you wind up with this scenario here. This is showing a bit more than one additional register, although it's a little harder to see. But because we have this static allocation of threads and registers to threads, by just adding one more register, like instead of using 27, we're now using a 28th register in our code. We could go from being able to fit 4 thread blocks to 3 thread blocks. If 4 fit exactly perfectly on the device, and we then added one more register to thread, again, one more temporary variable in your code. Again, the compilers can do lots of magic things to minimize register usage and all that, but generally, more variables means more register usage in your code. In doing so, we've now decreased our utilization by a fourth, right? And that could be significant from a performance perspective. So that's one of those limiting resources here. We have this SIMD model that allows us to do everything from a single thread's perspective. That allows us to switch state very easily because going from thread A to thread B or thread block A to thread block B just means changing a couple base addresses in our register file. But because of that, because there is no software managed context switching of a significant sort that we're used to when you take your operating systems class, you hopefully learn a little bit about that. I keep saying that, but I don't see heads nodding. So I really hope you cover context switching in an operating systems class. Otherwise, I don't know what the point of the class is. But having said that, you have that simplified way of then switching. You're changing some base address pointer that changes your address calculating to the register file. But the implications there are, as the programmer, while you may not have explicit insight into exactly what address pointers are being calculated, very small changes to your code, in this case, adding one more variable to your CUDA code before it gets compiled, could lead to significant, if not performance differences, utilization differences in the device. We go from fitting 4 blocks to 3 blocks. That would be a significant difference there. That's an extreme scenario, but it's something to keep in mind as you start to play around a little bit more with CUDA. The other important piece of terminology, this was originally kind of a hidden architectural detail, but if you look at the CUDA programming guide now, they do explicitly talk about this. So it can be a little confusing, but we have, from the programmer's perspective, we have this multi-dimensional layout of threads. I don't want to complicate the matter. I'm going to use the terms precisely, and then we can go back to the preceding slides if there's some confusion here. You have organization of threads into a block. That is the individual schedulable unit of threads. And when we specify a CUDA kernel and we launch it, we say, here's my block dimensions. Here are the threads in a block, X, Y, Z. Then within our higher level parallelism, we have multiple blocks that are then organized into what's called a grid. So you have threads in a block and blocks in a grid. That is the programmer's organization of work. And if your code doesn't have such explicit amounts of parallelism, you're going to be limited in terms of how you're going to organize those threads into a block. So that is the programmer's view of thread organization. And that block, which could be three-dimensional, but you can think of it just as a single-dimensional case to keep life simple right now, is our schedulable unit of work. I have the SMs, and I'm putting blocks on the SMs. And I'm putting as many blocks, generally the scheduler will, as many blocks on an SM at a time as will fit. One of the limiting resources would be registers. If I can fit 4 blocks in there, I put 4 blocks on there and schedule it at a time. If I can only do 3, I do 3. That is the programmer's view of parallelism and the general assumptions you can make about how things will get scheduled in parallel. In terms of at runtime, this is an implementation detail now, there's this concept of a warp. Um, I don't especially love the term warp. It's referring to not like warp drives or things like that. Referring to, it's something of a loom analogy where you have these all individual strands and you're picking at the strands and you're making a carpet or something. So that is the analogy they're going for. I have a picture that attempts to show a loom and what a warp on a loom looks like. A little outside my area of expertise, but the term warp is referring to, as the block is being scheduled, there's this unit, and so far, for at least the last decade, the unit of execution that gets scheduled at a time is 32. So the multiprocessor takes the threads that are part of a block and is going to create the threads to execute, manage, and schedule them in these groups of 32 parallel threads at a time, and that's what's referred to as a warp. That's an extra implementation level detail that also has some big implications on performance. So you have all the threads in a block, and it would be presumably much larger than 32. Let's say it's 1,024 threads in an individual block. And then you have a certain number of blocks within a grid. And that's, who knows, it depends on your application, how many blocks you have in a grid there to get to your tens of thousands or hundreds of thousands of threads in total. At runtime, blocks get scheduled on the SMs. The SMs then take those blocks and peel off 32 threads at a time. And that's our individual executable unit of work for these SIMT architectures. That's what's referred to as a warp. So it's an implementation level detail that is something we have to be somewhat cognizant of. If you're not aware of your warps, you'll just have slightly less efficiency in your implementation. It'll still work correctly. But the idea is now there's this extra level of limitation of what happens in a warp. Individual threads composing a warp are going to execute at lockstep with each other. So they're going to start together at the same program address. Depending on which generation of device you're actually working on, they actually even share the same physical program counter. That has changed, but only in the last 2 years or so. So at least originally, when this diagram was created, they actually would share the same exact program counter, all 32 threads in a warp. So when a multiprocessor is given one or multiple thread blocks to execute, it's going to partition them into warps, and then it's going to be a custom piece of hardware referred to as a warp scheduler that's going to determine what is ready for execution next. And that's what's being shown here in this picture, is that you have a pretty traditional looking SIMD style pipeline here. Instruction fetch, this should sound somewhat familiar, right? Instruction fetch, instruction decode, register read, some parallel execution, and it's intentionally showing 8 lanes in an 8-way SIMD architecture here. Memory stage, potential write back stage here. An entire warp is what's going to be executing at a given time. So every 4 cycles, because we can do 8 things at a time in this implementation, every 4 cycles we execute an entire warp. Because for each of those 4 cycles, we'll have done 8 of the threads of a given warp. Because we have an ALU, at least in this generation of device, that allows us to do 8 things concurrently. And so when we talk about there being a thread warp that is available for scheduling, It is really no more than just a small amount of metadata keeping track of what is my current program counter, what is my thread ID and stuff like that. The stuff that we encode directly into each kernel to let us know what math in particular should this individual thread be working on. And when it gets time to execute, the reason this works and the reason we can do 32 threads without having to really worry about context switching between them is because, for example, we have this instruction cache, but we have just a single kernel, right? And the kernel's written from the individual thread's perspective. So the instruction cache should work just fine because even for all the threads in a given warp, they could be on the same exact program counter value. But for all the different thread warps, while they may not be perfectly in lockstep for each other, you can have branching within your warp. You can have certain warps that have an instruction, a data cache miss, and other ones will have data cache hits, so they may get out of sync with each other. But they should be roughly in the same region of your block of code at any given time. So when it comes time to execute that and to go from one thread warp to the other, effectively, this implementation becomes effectively stateless here. It's taking a program counter, it's doing the work associated with it. Right? This doesn't show, that register read has to take more information than what's directly encoded in the assembly instruction. We have to change the base address into our global register file here, but otherwise, ultimately, there's little to no state associated with this. This is what allows us to schedule it very effectively. In a traditional implementation, think back to your scalar 381 processors, or heck, think to your implementation right now. Instruction cache, decode, register read, ALU. You do a load or store. If you have a miss in your data cache, which is happening to us a lot, right? What do you do in your current implementation? Because we're doing things in a scalar manner. We wait, we stall. We sit there until that data cache miss gets resolved, and finally the cache lets us know, yes, I finally have the data you were interested in. With regards to our NVIDIA style CUDA GPU implementation, the beauty of it, and the reason it effectively works, is we can basically entirely hide this miss. Warp comes through, all 4 blocks of it, or 32 total threads are executing, and it's very possible that we get a miss, right? If they're executing in lockstep, they're going to be doing the load or store instruction in lockstep. We will have 32 loads or stores happening, and they will be happening to different addresses, right? Because presumably each thread will be doing different work, slightly different work, different indexes, offsets into an array in memory. So they'll be doing the same work but looking at different pointers in memory. So it's possible 32 threads come in, maybe 31 of them have a cache hit, but the 32nd has a cache miss. We would, in theory, then have to wait for that cache miss to get resolved. That could be 300 cycles. Instead, as part of the scheduler, we just say, okay, send off that request to DRAM, and put this thread into a separate queue. And this is sort of the busy thread queue or the waiting for memory thread queue that we would have over here. And from the perspective of the processor, we don't care, right? Let's just go to the next one. Whatever the next one is available, have that one execute next. From the perspective of getting, parallelism out of your application, getting good performance back out, as long as this pipeline is full, as long as this pipeline is always doing valid work, well, you're doing as good as you can do, right? You're keeping your ALU as active as you're possibly able to keep it. So from an efficiency perspective, it doesn't matter if we're executing thread warp 5 or thread warp 7. As long as we always have one available to execute. And hopefully that part makes sense. So this idea of, even though we may only have hundreds of these CUDA cores or streaming processors available to us at a given time, we want to have thousands to tens of thousands to hundreds of thousands of threads so that when they get collected into warps, and we know that, cache performance is what it is. Maybe if we're lucky, we hit 97% cache performance here. For that other percentage of the time, when these warps are waiting for memory to actually return and to get us the result that we're hoping to have back, as long as we have one other warp ready to go, then we're doing as well as we can do, right? Then our GPU is as busy as it can possibly be, doing valid work. We're getting, hopefully, the speedups one would expect by having that much computational density on the device. There's an extra little bit of mechanism then happening here. This is probably where some of that real NVIDIA expertise comes into play, where this is a lot to describe this logically is a pretty straightforward thing. If cache miss, then put warp into idle or busy queue, and you know wait for DRAM to return value. In practice, that's probably a pretty complicated piece of hardware to actually generate, but that's what's happening. So thread warp 5 missed in the cache, has to access main memory. Eventually, that main memory will return. It'll take 300, 400 cycles. As long as that in that 300, 400 cycle wait, we had enough happy work for the GPU to be doing, well, then we're all good, right? We've completely amortized or completely hid that latency associated with missing in the cache. Because while we were waiting for that miss to occur, the GPU was doing work. At least this streaming processor, had enough thread warps that were doing other things, either hitting in the cache or not needing the cache and just doing ALU, R-type instructions type of work, and it was sufficiently busy. It was at 100% busyness. Eventually, there's some mechanism, and again, logically, it's easy to describe. Architecturally, I think this would be a non-trivial thing, but logically, at least, eventually that request to memory returns back. Here's the memory you needed, or your write to memory actually completed. But for loads, it'd probably be more important here. And then this thread warp gets reallocated into the ready queue, gets moved up here. So that's why you need to have that many threads. Long story short, there, so that this queue has enough stuff available that you can tolerate a certain percentages of your misses and still have work ready to go. Any questions about that before we continue? So when we talk about SIMT and what makes it different than SIMD, this is the big picture of it. Not the fact that it's 32 and that what makes a warp. That's an implementation detail. But the idea that because all these threads are doing the same work, they could be at different places from each other, but they're all doing the same work. Because of that, and because we want to have way more threads than we have schedulable resources here, we can tolerate things like missing entirely in our cache and having to go off to DRAM. Versus if we just had a single thread of execution and we missed in the cache, it defeated the purpose of all that parallelism, right? Because we're sitting there idly waiting. That is what's unique about this style of architecture. I mean, and the other detail is what's being shown here, right? This single pipe, being shown here. Again, because it's a single instruction stream that simplifies our implementation of our instruction cache and our program counter and even the decode logic, right? That's also the case in SIMD, but in this case, it's even more so because our multiple threads are all accessing the same pool of instruction memory. The only difference is we're doing some unique indexing to actually get the right values in the register that particular thread is actually needing at one given time. Okay. Well, I think I already handled this, right? So that this is the big concept and why one wants to very carefully, manage the number of threads. Why having a single threaded kernel doesn't make a lot of sense in an NVIDIA device here. It's because of this issue that I think I already discussed here. So in accessing the memory hierarchy, you have that hundreds of cycles of latency associated with that miss in the cache and having to go off to off-chip DRAM. As long as we have enough warps available so that there's always one available for scheduling at any given time, then we can tolerate a lot of those misses happening. And a lot of warps can miss and be put in this kind of busy, not ready to execute queue, as long as we have enough total so that eventually we're staying on top of our latency of DRAM. It's a latency hiding issue, right? You can think of it as amortizing the cost of accessing off-chip memory, or just hiding the fact that there's a several hundred cycle wait. As long as there's work to do, who cares that some threads had to sit and wait? That's the warp, that's the loom technology and the visualization of it there. Doing the back of the envelope math for this is a little tricky, but in general, the big picture concept is that this SIMT or SIMT technology allows us to effectively do zero overhead warp scheduling. Going from warp A to warp B is intended to be a trivial thing. And because they're all executing the same thread, right? It's only one stream of instructions we have here. The only difference could be from one warp to the next. What program counter are we currently at? They're not going to be entirely in lockstep with each other, but they're probably not going to be too far apart either, because these kernels tend to be reasonably sized at any given time. You're not going to be 10,000 instructions apart from each other. You're going to get very good instruction cache performance. You have this queue of available ready warps ready to go. All that would mean would be, here's this warp ID, here is the program counter that we're currently at, maybe some other metadata associated with that, like our register file offset. When it's time to schedule, next warp in. When it's an instruction or data cache miss, and we're going to have a multi-hundred cycle latency associated with that miss, go in the next queue. We'll wait for those hundreds of cycles. Next warp in. Obviously, if every single warp misses in the data cache, which could be the case at initial startup, right? There's going to be that kind of warming up of the cache issue. That's always the case, right? It's not magical in that sense. If every single thread misses in the instruction cache or misses in the data cache, then you're not going to be able to hide that latency, right? Because they're all going to be missing and all going to be waiting. But if you have enough work in the steady state, in the general case, as long as that next one is ready to go, you've kept the streaming processor, the CUDA core, sufficiently busy that it's been able to hide that memory latency. And in terms of the instruction scheduling, you wind up with something that looks, like the following, in which, in terms of what's executing, at one given block of time, you may be executing warp 8 instruction 11. And there's no requirement that it necessarily switch from one warp to the next, but due to the pipeline nature, that's a very natural way of doing it. So you may be warp 8 instruction 11 followed by warp 1 instruction 42. I know these are arbitrary, but from each scheduled block of time here, every 4 cycles, you'd be switching from warp to warp and executing from the same instruction stream, just from threads that are at different points of their execution. Don't think we need to take a break and try to do the back of the envelope math for this, but that is the math that one has to do when figuring out how many warps is a sufficient number of warps to keep things busy. So if we assume there's a 400 cycle, memory latency, memory latencies aren't always the same. It's deterministic, but it's based on what sequential addresses versus non-sequential addresses. It's a function of next level cache as well. So we can't always say it's always a 400 cycle latency, but for the back of the envelope math, that's sufficient for us. Take a moment and think about it. But if we had to fully tolerate a 400 cycle latency, and every cycle we're getting 4 warps and 2 independent instructions per warp for every given cycle, well, how many warps would we need total? If it was an instruction or data access, every single instruction, it would never work, right? We would always have that 400 cycle latency. Excuse me. What the question's asking is, if our load, meaning given the percentages of load instructions in our instruction stream multiplied by our effective cache hit rate, leads to a 1 out of 64 miss rate. So for every 64 instructions that results in a cache miss having to go to off-chip memory, well, then how many warps would we need to have? And the math is a little complicated by the fact that we're doing 4 warps at any given time. So for every 4 warps, for every cycle, we're executing 4 warps and 2 such instructions per warp. That means 8 instructions we're executing every cycle, and every 64 instructions we're having a miss or need to access off-chip memory. That means that every 1/8 of the time, we're having to tolerate a 400 cycle memory latency. And then to tolerate a 400 cycle memory latency, you need to have work to fill up those 400 cycles. So 4 warps, 2 instructions per warp dispatched every cycle, with a miss then every 1/8 of our dispatches, meaning we're going to need to have 8 times 400 total warps available at our schedulable unit here. Anyway, we could have worked out the back of the envelope math. Um, in general, as we're determining how many threads we will have for our application, there's 2 competing kind of interests here. One is certainly, what is our parallelization? For the application we're executing, how much parallel work can we get out of it? And the second then is, can we get enough work on the device to make it worthwhile? I think based on what I've explained so far, because we don't have any of the CPRE 581 mechanisms for tolerating branch instructions and branch misses, branch prediction to tolerate, branch control hazards. We don't have a lot of the super scalar combining instructions and trying to execute them concurrently. None of that mechanism is in place. The trade off in the design of these devices is put more ALUs as possible, as many ALUs as possible, and dedicate as much of our transistor budget to computation as possible versus handling control. Because of that explicit trade off being made here, as we're designing our application to execute on them, we could do an application with one thread. CUDA doesn't stop you from doing that at all. It doesn't give you a warning or anything. Here's my kernel. I'm going to execute it with one thread. And right for testing, that probably makes a lot of sense to make sure your code does what you think it does, and etc. But it's going to be very painfully slow for that reason. It is a very light core, these individual streaming processors. It can do this kind of 8-way SIMD type of execution. But if you don't have these hundreds to thousands of threads to create enough warps to keep the warp scheduler sufficiently full at runtime, you're going to lose a ton of the benefit of having all that parallelism. We already see that in our implementation. We have parallelism in our instruction stream for our vertex and our fragment shaders for our MP3 and MP4 logic. And a lot of that is arguably wasted, right? You have this parallel stream coming in, and then you sit and wait for the cache miss anyway. What was the point, right? What was the point of having as much parallelism as possible in the instruction stream if they're sitting idly anyway? The correct approach to that would be to schedule much threads of work as possible on the GPU at a given time. That's what's happening here in our unified shader architectures as well. So in general, all of the things you would learn in the CPRE 581, which is being offered again next fall, are appropriate. There are ways to understand how to squeeze out more performance out of our generally single instruction, single data flow of our scalar sequential programming languages. And there's lots of tricks we can continue to learn and use, supporting deeper pipelines, supporting parallelism within the pipeline, and the trade-offs involved with that. Very important stuff to learn. When we look at the GPU space here, because of our, the evolution of it, right? The evolution of there is a lot of parallel work. The vertices, by and large, can be executed in parallel, can be transformed in parallel. Same with the fragments. We can get to thousands to millions of individual units of work pretty easily with traditional graphics applications. The GPU has evolved to support that class of applications, and also now in supporting compute applications, the general purpose compute applications here, we have a very similar set of restrictions. So while you see CUDA and NVIDIA used for all these HPC workloads, the type of parallelism model that tends to work very well on them tend to be at the order of magnitude that was originally inspired by our graphics workload. Can you find a million things for me to do in parallel? Only certain applications does that make sense for. When you can find those applications, then you tend to have a scenario in which you've just blasted the GPU with a million threads in whatever organization makes sense for your application's perspective. The GPU is able to be kept busy because it can do things like switching from one thread block or one warp to the next warp with effectively a 0 cycle overhead. Next warp up, as long as there's enough so that one of the warps is always ready to go at any given time, you can have things like a 400 cycle memory latency with no real penalty associated with it. That is unique. There is really nothing in the traditional CPU pipeline research and implementation space that allows you to truly hide, 16 straight data cache misses, whereas in your GPU space, because of the thousands of threads, you can effectively do so if you have enough work. I mean, that's what makes it cool, too. I mean, honestly, it's different. It's not one as a replacement for another. If the work I need to get done is inherently sequential, written in a sequential programming language with effectively minimal, parallelism inherent in the algorithm, your GPU is not the right choice, right? So it's not a fix all for all compute workloads. It has to be something that effectively looks like this. And then having said that, this idea of occupancy or determining what the upper limit of what can get scheduled at any given time, how many thread blocks can I fit, how many warps can I have in parallel on an SM at one given time, becomes actually a first order design consideration for coding in CUDA versus, right, when you're in other programming languages, some parallel frameworks do have you be very explicit about the total number of threads, but usually not to this degree, where if you're looking to eke out performance, you want to look at your code and determine something you would normally never really even look at. How many registers am I using in my code, right? We write code, we never really think about that. But when we're working with CUDA, always get things working first and then worry about eking out that much more performance. But looking at the hardware limitations, which is very device specific, but looking at the hardware limitations and then what level of occupancy is possible for my application can help you get significantly better performance than just guessing at what the right number of threads would be for your particular application. So there's some hardware limitations. So physical hardware, NVIDIA talks about sort of compute capabilities, which is really describing a hardware spec for things like how many, what's the upper limit on the total number of registers that each thread can support, uh, how many threads per block. I mean, as we've started to implement things like this ourselves, we can kind of understand that at some point, some hardware designer had to make some decision of, you know, well, how many blocks can fit on an SM at a time? 16 seems kind of arbitrary. Presumably, the engineers at NVIDIA know what they're doing and have profiled workloads and have determined that that's a reasonable upper limit. Likewise, 2048 threads per block. This is for Kepler class devices, so kind of old now, but third generation unified shader architectures. Um, Presumably, there was an engineer who realized, well, we could do a 32-bit register for storing this information, but it would actually make all these other FIFOs that much bigger, and we're starting to miss timing, and we know how painful that is. So if we keep that to be an 11-bit value to keep track of our total number of threads per block, um, all sorts of other nice little optimizations can happen elsewhere in our pipeline. So there's some physical upper limits that is just a generation by generation distinction. Uh, Whatever device capability you're working on, it'll tell you what those upper limits are. And then there's the characteristics of your application that you could then plug into this CUDA occupancy calculator. There are, in fact, programmable ways in CUDA itself as you're writing your code. There's functions you can call that basically can tell you the occupancy, but actually, um, maybe it's an old school way of doing it. But the actual CUDA occupancy calculator, I think, is actually perfectly fine. It takes a little while to get used to. So I don't know how well you can see this on the slide behind me. It'll be fine in the recording. That link on the slide is valid. It's just a straight Excel spreadsheet that you have to enable all sorts of scary, permissions on to be able to run the macros that are encoded in there. It's pretty harmless, but it gets you a feel for both the generation of architecture you're working on, which NVIDIA tends to talk about it as compute capabilities. That's the description of what generation of architecture are you working on. There's a big table they provide of there's CUDA functions as well, but there's a big table they provide that says if this is your hardware, here's your maximum compute capability. So you can go from there, and they tend to be backwards compatible for the most part. But you would specify first, okay, what is my hardware? Again, it's not for whatever reason, it's not as simple as saying, here's my particular device. You have to look up what compute capability that would correspond to. There's then some upper limits based on which GPU you specified. So things like, well, threads per warp is a given. I think that's 32 for any of our compute capabilities for any of our different device generations here. But things like the upper limit of the total number of max warps per streaming multiprocessor. For this device, it's set to 64. I don't have any of these memorized. As I increase that value, some things change, other things don't. So some of those seems like they've been pretty constant over time. But as we go to the latest and greatest, and you get your Volta class device, now you can go up to 48. Now you can go down to 48 warps per multiprocessor. So there's some trade-offs associated with that. Um, these other things in the gray boxes here are just kind of the physical upper limits. And I think, given our experience so far this semester, we can't say for real specificity, why exactly our maximum thread block size is set to 1024. We can kind of figure out why that's the case, though, right? Without knowing exactly why that happened, we know that that information has to be directly encoded at runtime. There needs to be FIFOs and registers and configuration registers and the like that are storing that information. And as we try to squeeze one more streaming processor onto our device, the NVIDIA engineers were trying to fit one more streaming multiprocessor onto their device. And there's those trade-offs involved with it, that as you have that level of bits of encoding for for this information, uh, it's got a multiplicative effect, right? That by increasing the size of that register, I have to store that information throughout. I probably have to do some multiplication on those registers to actually get multi-dimensional indices into our thread blocks. There's a lot of extra things that are happening with that encoding. So it's hard to defend any individual particular value for the physical limits for our particular compute capability. They seem arbitrary to us, and they kind of sort of are. But we understand why there are those limits, why not everything is just a 32-bit limit, why you can't have 4 billion threads per thread block. The reason would be, first off, an understanding of the applications and why they would even need that level of parallelism, but also understanding that those physical limits, um, those uh, descriptive registers associated with the architectural design have this effect on our critical path, on our total resource usage, and the ultimate size of these streaming multiprocessors. So this is kind of a fun thing to play around with. I think it's worth doing once. So the exercise, and we can do it together again. Every time we've tried to break into groups, it didn't go all that well. Um, Take a moment though. So given compute capability 3.5, which is Kepler, um, it's the hardware we have available on the Xilinx machines. Um, Given compute capability 3.5, if I can get my mouse here, I'll switch back to 3.5. Certain things are physical limits again. We've changed it. We've gone down to 3.5, and we know we can only fit 16 thread blocks on a multiprocessor, and a total of 2048 threads, which would be a maximum occupancy of 64 warps. That's just simple division. That's 32 times 64, right? To get to that number of total threads. Occupancy is not the same as performance, and I keep just being kind of hand wavy when I talk about that. But the whole point of occupancy is this again, right? So when you think about occupancy, think about this. Think about the fact that for this whole idea to work, we want to have as much here as possible at one given time. So more is generally better. If you can fit more threads on an SM at a time, this is all very general, I understand, but if you can fit more threads on a streaming multiprocessor at a given time, there's no guarantee that your performance is better, but you're able to hide latency better. More is generally better, but we can't say that. We certainly can't say that if we have 10% more occupancy, we have 10% more performance. That is a much harder thing to try to predict. There's weird tail effects of scheduling threads. It's actually very hard to truly know the performance until you measure it. But occupancy, more is generally better. So one could think of your goal if you're running on a GK110, 3.5 compute capability. Feel free to check your own devices at some point and redo this example with your own GPUs, if you have an NVIDIA GPU at least, and grab this spreadsheet. Um, we have an upper limit, and you can think of your goal is to figure out for your application, can I get to 64 warps for this case? Can I get to 2048 threads for my application? 2048 is our best case. That is a physical limitation. You cannot do better than 2048, but you can do worse than 2048. And that's the example I was attempting to show you here, and I'll go back to it now. So for 3.5, and assume we have 382 threads per block, and as many blocks as needed, with 9 registers per thread and 4192 bytes of shared memory per block. That is what we'd have to enter. Now, you may say, well, how do I know I have 9 registers per thread? Well, the compiler will tell you that. You have to pass it a flag, and it'll spit out, or you can look at the assembly generator. It'll tell you the kernel that you've written that we're going to execute is going to need 9 registers per thread. Roughly 9 sort of independent variables needed to execute the code that you have, right? It's never that clear. You can't look at variables and know exactly how many threads or how many registers are associated with it. But in this case, the compiler is very good at doing that, doing register allocation, telling you exactly how many threads that you or how many registers it's going to need. So this is an arbitrary example, but assume you've organized your threads into a block and it's 382 threads per block. And we'd go and actually enter that in. And per thread, we have 9 registers. And then finally, we haven't talked that much about shared memory yet, but that's just yet another shareable resource here. We have 4192 bytes of shared memory per block. May sound arbitrary. and that's okay. It is. The question was asking, let's just take a moment here. You could open up the spreadsheet and look at it yourself. Um, the question's asking really, what's our limiting factor here? We do not get to 64 warps or 2048 threads. Again, you're just multiplying by 32 there. We're not getting to 64 warps, which all those caveats taken into account that it doesn't mean our performance is 10% worse because we only got to, 58 warps. But presumably it's not as ideal to be in that case. We got to some 50, it should tell us the actual number. We got to 60 warps. We're at 94% occupancy. The assumption of this exercise is we wanted to get to 100. And so I think it's a valid assumption. We wanted to get to 100% occupancy. We have this massive device. Let's keep it full of warps. We got to 94%, which, if you get a 94% in your classes, you're an outstanding student. If you get to 94% occupancy, uh, you're only an okay student. What's the limiting factor here? The charts will tell you, but to what extent you can actually see that on my screen versus opening it up locally here. What it's showing is for different values we create here, both of impact of varying our register count. Currently, register count is set to 9. There's an upper limit of 256. That's another one of those physical limits, kind of 8-bit address port to the register file, presumably, um, or 8-bit offset field to the register file. According to this chart, I'm actually as good as I can be. The impact of varying register count per thread. I can drop my register count to 0, and it's not going to do anything. I'm still at 60 warps. Conversely, if I do increase my register count significantly, I'm trying to think what's on that slide. If I actually increase my register count to 96, now my efficiency has gone, or my occupancy has gone way down. Now I'm at 19% occupancy, struggling a little bit here. For whatever it's worth, you can't say necessarily the performance is 1/5 as good as ideal for our application, but we do know that if our goal is to hide memory latency by having lots and lots of warps, we're probably not doing a very good job of it here. So the answer is not register usage because we're doing okay. We're at the top of that particular chart there. Um, let's take a look at block size, right? So if we were to change the number of threads per block and potentially increase it here, and I go up to 512 threads per block, I've actually increased my occupancy back to 100%. The kind of funny thing about that, though, is it's really a matter of how these things kind of divide into each other. Because what that chart is showing, this particular chart here, and it's a little misleading, right? It's hard to imagine how I would have increased my threads per block while keeping my shared memory per block the same. That would require a fundamentally different implementation of your kernel here. But what it's showing is kind of unexpected kind of relationship between our block size and our occupancy here. It's not as simple as saying more threads per block good or fewer threads per block bad or vice versa. It really depends on how these resources kind of divide into each other evenly or not. And we wind up with a scenario in which we were at, what was the number, 382 to start with? I think that's where we started with. If we actually drop that thread count back down, we could presumably then support more blocks at any given time and get back to 100% occupancy there. So again, from the CUDA programming perspective, there are API hooks to give you this kind of information. Um, it is possible. I mean, the code would, maybe if this is your day-to-day full-time job, you could write code that queries the compute capability, checks the occupancy for a few different options, and basically in your code re-implements this spreadsheet. In my experience, it's been useful as kind of an offline analysis tool. I have a belief in how I can parallelize the application. It works. Get something that works and is correct to begin with. I now want to squeeze that extra bit of performance back out. I can look at the occupancy and realize if I'm really suffering there, here are some simple things I can do to change my organization. Because otherwise, you will certainly find this the case. We have this multi-dimensional layout of threads in a block, blocks in a grid. It's kind of arbitrary feeling, right? For the kind of applications we want to use, it's really hard for us to know this is exactly what my thread block should look like in terms of my thread layout. Likewise, how many blocks I should try to organize and launch at any one given time. You can do trial and error. That's also a very valid approach. That it's a multi-dimensional search space, but it's not infinite. There's only so many possibilities that will make sense for your application. If you're not sure, try them all and then stick with the one that works just fine. You look at some of the NVIDIA CUDA SDK examples. Some of them are trying to be very clever about understanding occupancy and performance of the underlying device. Others appear to just have some magic numbers baked into it that with 47 blocks in this grid, it gets the best performance, and that's what they use for that particular instance. Both are fine, but this is a pretty straightforward offline way of analyzing and realizing that, this idea of a thread warp as the individual schedulable unit here has direct implications of performance that we don't have to write our kernel to be cognizant of what our warps are doing, although there's some caveat there as well we'll talk about on Thursday. But our awareness of the total amount of schedulable work can have a direct impact on performance. That doing something as simple as, going from 256 threads per block, well, 256 threads is good, 300 threads should be better. And it turns out for this particular application, knowing nothing else, all else being equal for it, we've actually decreased our occupancy and presumably decreased our performance, although not necessarily so. How are we doing today? We okay? Been very quiet. This is all just a fire hose of information, and this is the other prep week issue, right? You finally get to the fun parts of your course, hopefully for your other courses as well. And now we're out of time. There's no time to have an assignment on this. We need a 580 class coming after 480, where we just continue on and we just learn the next step of both graphics algorithms and get some more experience with CUDA. Um, Maybe one day, not not this year. I talked about the assembly format, the kind of virtual ISA format. Virtual in the sense that it's not directly a one-to-one correlation with the final microcode uh, running on the device, but it does give us insight into the type of code that will actually be running on our device. This is our parallel thread execution assembly, and it should look pretty similar, familiar to us with the kind of things we've been playing around with this semester. You can just tell the compiler that when it's compiling to actually uh, spit out spit out that assembly code. So the dash dash PTX example here. So for this CUDA kernel that I have here, we've already opened up and looked at this one before. This is a matrix multiplication kernel, and it's meant to be a pretty trivial version of it. It's doing some things we haven't yet talked about yet, but it's copying into shared memory, and then it's doing our basic multiply accumulate operation to get a matrix multiplication here. So this is the actual kernel for it. Very common with what you'll see in kernels, which is a decent amount of bookkeeping code. Figure out where I am inside my multi-dimensional layout of blocks and grids. In this case, it's matrix code, so having this two-dimensional layout kind of makes some sort of sense, a dot x and a dot y. Figure out what work I have to do based on what those assigned indices are going to be for my particular thread running at one given time. And in this case, this is something we haven't talked a lot about, but copy into shared memory so we have less of an impact of cache. So pay a little bit of penalty to begin with to do a whole bunch of loads. And then when it comes time to do the execution, you've grabbed that block. You can now do that execution fairly effectively. When they're all done, write it back into our main memory there. In terms of the actual math that's happening here, it's no different than any C code or C++ code you would presumably write to do the same. That there's a lot of memory management going on. The main loop is a multiply accumulate operation because that's always what we're doing here. We're doing dot products, right? So we're taking the row and we're taking the column and we're doing a dot product and we're updating C of ij based on C or A of ik times B of kj. In terms of what got generated for the assembly, well, it's an assembly format and it's an auto-generated assembly format, so it's not necessarily meant to be super easy to read at first glance. Um, Tells you capability version and I think version of the compiler here. Um, It has a lot of things that should look somewhat familiar as we've been looking at our own SGP assembly code here. There's only so many ways to do the kind of things that we've been doing, right? We first have to calculate an address to do these loads and stores. So moving some constants, doing a multiplication, uh, shifting by 4, right? All these kind of things should look kind of familiar to us, right? Right? We're trying to figure out our address in memory, given a pointer I and a pointer j, or an index I and an index j into a two-dimensional structure. Any assembly format in the world is going to look roughly similar for doing that, right? And then set predicate. We'll talk about that probably on Thursday at this point, and then do a branch based on that. Finally, ultimately, there's going to be the actual uh, work that's being done here with our multiplication instruction. Let's make sure we find the right part here for this. Here it is. All that is our kind of bookkeeping and copy code. Here's our main. This would stand for auto-generate basic block of the code. So our main for loop that we have here in the code. Do some load, do some store, do a fused multiply add instruction here. So do my SIMD style vectorized operation. And there was some pragma to unroll that loop, so it's actually unrolled that loop entirely. If we look at this, a little bit of compiler magic saying, we as the programmer, it's easy for us to write this as a for loop. For loop is a very logical way to describe what we are trying to do here, right? But you as the compiler, get rid of all that for loop stuff for us, because it's a loop that's iterated based on a compile time constant, and consequently, when we look at the assembly code, there's no loop here at all, right? It's just doing all of those operations, and then finally store the result when we're done back into main memory there. There's some value in looking at your PTX assembly, just like the same level of value you get in looking at any auto-generated assembly for code that you're writing. It gives you a feel for what optimizations are being applied. You can get a better feel for the total number of registers that are being used, although there's separate tools that will directly tell you that. It should give you a feel for how much branching there is in your code. Are you going to have control hazard style problems in the execution of this? Um, and just gives you a general feel for the complexity of the kernel that you've created. Doesn't tell you the performance of it, but at least you should look at this and be able to say, well, it looks very similar to assembly that I've seen before. In this case, the other layer of complexity is it doesn't directly translate to the final assembly. NVIDIA calls it their SAS assembly format that actually gets run on the device itself. But there's a pretty close to one-to-one relationship that happens at the driver where it gets just in time kind of transcompiled or reassembled to that final format that's being executed there. The driver then would have some sort of assembly cache as well. So that happens maybe the first time your code gets executed. Second time, it doesn't actually need to do that assembly process. Yes, so you can specify PTX and NVCC. The same compiler can take PTX assembly as an input to it. We generally don't do that. I mean, you can, just like we generally don't do a lot of assembly programming, but one can do so. And part of the CUDA programming guide is also a PTX programming guide that provides you some, at least, starter hints. I don't tend to see PTX code used in any production environments for the same reason. You don't tend to see a lot of assembly code used in production environments. Where you do tend to see that is when there's an explicit need for SIMD execution and they're squeezing out an extra little bit of performance. Well, in this case, that's what CUDA was designed to do, right? So you don't tend to need to do that much development directly in the assembly, but you can. It's perfectly valid to do so. I think we've covered what it means to launch our kernel, but I'll show at least an example of that. Let's leave things here for today, given the time that we have available. On Thursday, and I've made the offer that we can keep going as long as possible into the summer if we'd like. But I definitely wanted to get us to some of the examples of actually doing this programming in practice. At the very least, if not, I'll provide the slides. You can look at things offline. I've mentioned the fact that there's many different books one can purchase, or grab from the library on CUDA programming. I actually think the CUDA programming guide, download the SDK, which gives you about 70 different examples to look at. Download the actual PDF for the CUDA programming guide. It's a really good way to get started. Oftentimes with any new environment, the most painful part is getting, hello world to compile, right? Making sure your make file and associated compilation infrastructure is set and ready to go. But once you have that ready, um, this is something that is rising seniors and graduate students you should be able to handle in terms of the syntax associated with it. What I'll try to cover more on Thursday are some of the additional architectural implications of this style of programming, how we can take advantage of some of them, how we some things to watch out for as we write our code in certain ways. We won't get to a lot of actual doing of this semester. Um, there's still room for that next version of this class. This is also just a great thing to kind of explore if you wanted to do so via independent studies. We have some fun hardware that you can play with regards to that, both in the embedded place as well as in the HPC space. So let's leave things here for today. Thank you for everyone who filled up your course evaluations. If you have not done so, please do so. I want to get to 100% for that. Um, Otherwise, I'll see people in lab tomorrow for our very final scheduled lab section of the semester. I'm available for office hours today at 11, so stop by if you want to chat then. Otherwise, I will see folks on Wednesday. Thank you.